Welcome to Bass, the band adjustable signal sculptor, also known as Schmunky Q. I'm your host, William Brooks, joined by my teammates Tyler Zoden, Jack Ellis, and Shaylin Cypher. For our project, we built an equalizer pedal. An equalizer pedal takes in a single audio analog signal and then allows you to individually mix the different frequency bands to sculpt a desired output signal. For example, say you had an input signal from a guitar or other instrument, and you wanted to filter out the bass or amplify the treble frequencies. An equalizer pedal would allow you to do that through the adjustment of various knobs and dials on the pedal. We chose to build an equalizer pedal because it perfectly represented the overlap of our interests of music and also with the content from signals and systems. An equalizer pedal is a technology that already exists. We wanted to introduce a certain amount of novelty to this project. We did this by making our own design so that it fit perfectly to the guitar of one of our group mates, and two, we did this by introducing a visualization aspect that allowed the user to see the various frequencies being mixed in the signal. To start this design process, we first had our group mate play a sample from his guitar, which you're currently hearing in the background, and then we took that audio signal and did a spectrum Fourier analysis on it so that we could better visualize the signals and frequencies present. Once we completed the Fourier transform, we then had to decide how we wanted to design the pedal to capture these frequencies. We determined that from the transform, we wanted to design a 5-band filter that centered around frequencies at 100 Hz, 200 Hz, 400 Hz, 1000 Hz, and 2000 Hz. The general form of design that was finally chosen for the overall circuit was one where the input signal was fed individually into 5 different bandpass filters. These 5 different bandpass filters would then filter the signal based on the 5 frequency bands determined. Then those signals would be recombined through a summing amp, which had potentiometers in the feedback loop to allow for the individual gain of each signal to be adjusted. The output of the summing amp would then be put into an inverting amplifier to allow for the overall gain of the system to be adjusted, as well as for the signal to be corrected to the correct phase. After this general design was completed, research was done into bandpass filters, and it was found that the Salon Key bandpass filter would be the best filter to suit our needs. Once the general design was completed, the exact design had to be determined. The Salon Key bandpass filters, further research was done into all of them, and then a MATLAB code was written to determine the optimal combination of resistors and capacitors to configure the filters to the exact corner frequencies we wanted. In addition, research was done into the correct values of the resistors that needed to exist in the summing amp and inverting amplifier in order to have them exhibit the correct behavior in the system. The final circuit was then built in Multisim and tested extensively to determine its functionality. The signal was tested by inputting a chirp voltage from 0 Hz to 3000 Hz, approximately modeling the range of potential inputs. The potentiometers were then actuated to different values to test the filtering of both low frequencies and high frequencies. An example of a test done was what is on the screen currently. All the gains were set to 1, and the result was that the output nearly exactly modeled the input. Conversely, in the graph now seen on the screen, the lower frequencies were set to minimum gain, and the high frequencies were set to maximum gain. As a result, the higher frequencies are amplified, and the lower frequencies are attenuated. These are only a subset of the tests performed, but it can be seen from these tests that the high and low frequency content of the signal can be altered by the input from the user into the potentiometers. The aspect of this project is the visualization aspect. The visualization aspect reads the voltages at the various inputs to the summing amp and then displays them on an LCD bar in a bar graph format so that the user can approximately visualize the amount of frequencies constant in this current signal. Measured voltage signals are captured via analog peak detectors. The analog peak detectors then feed their signal into a microcontroller, which actuates the OLED screen. The microcontroller had to be programmed with the correct code in order to display the frequencies on the screen in the bar graph format. Further, the microcontroller also had to be programmed with a certain sampling rate in order to be able to adequately sample the analog signals coming out of the filters. On the actual pedal, the screen will sit at the top and will constantly display the relative volume and content of each frequency band within the signal. Once the designs were finished and all subsystems finalized, it was time to actually build the device. First, the filter subsystem was created on a proto-PCB board, and proper inputs and outputs were assigned electrically. Next, the actual housing was made. The actual housing was made by cutting out various pieces of an existing housing using a drill and a Dremel tool. Next, the various components necessary to actually integrate the circuitry with the real guitar and guitar amp were attached with glue. Finally, the screen, microcontroller, and peak detectors necessary for the visualization aspect of the system were all put together, and a proto-PCB board was made to house them. Once all the subsystems were completed, they all had to be integrated together. As is true with most engineering projects, this took longer than absolutely anything else. But after tons of effort and nearly 10 hours of soldering, it was finally time to test it. Introducing Base Monkey Q. Yes, unfortunately the pedal did not work. We can attribute this to a variety of factors, but most namely we assume it's to do with the integration of several systems and the tough connections that came with attaching all of them together. The electrical systems were built on proto-PCB boards, which are very tough to put together and require a lot of very difficult soldering. Additionally, we also did not use IC sockets when attaching the chips to the board, which potentially could have caused some heat-related damage or other damage that would have prevented the chips from functioning. Every subsystem of this project was tested individually, and they all did function. Likely the issue lies in just a simple matter of integration, and with adequate time and resources it could be debugged. But unfortunately, due to the tight time constraints of this project, we were unable to dedicate adequate time and properly figure out why this thing does not work. Ultimately, we do not feel failure of this project was a reflection of any lack of hard work from anyone on our team. Every group member contributed between 15 to 20 hours of work over the last 2 to 3 weeks. Unfortunately, it is likely just due to the too large of a scope and short time constraints that this project did not function. If we were to attempt this project again, we likely would pick a smaller scope to work with, perhaps a 3-band equalizer. We would also try to, instead of proto-PCB and electronics, we would get an actual PCB printed and soldered. Still, even though the project did not work, we still feel that our knowledge of signals and systems greatly increased because of this project. We learned valuable lessons about bandpass filter design and the designing of the equalizer pedal, and also lessons about sampling and the visualization aspect of the project. We also learned valuable lessons about physical construction of circuits, and that will likely be very useful in our careers and capstone during our 4th year. Finally, we would like to thank Professor Sirodopoulos for his continued support on this project. We would also like to thank Professor Williams for helping to fund our project and providing valuable insights. We'd also like to thank Professor Crockett for her valuable consulting on our project and feedback on our design.